Welcome back. The topic of this interactive video lesson is on rotations. Geometric rotations. If you are familiar with an analog clock, then you are familiar with the concept of geometric rotations. The hour hand is pointing to 12 o'clock. If the end remains fixed at point P, what time will it be after a 90-degree clockwise rotation? Notice the clock is divided into 12 equal segments. If an entire circle has 360 degrees, well, 360 divided by 12 is 30. So that means that each time the hand goes one space, it goes 30 degrees. So to go from 12 to 1 would be 30 degrees. To go from 1 to 2 would be another 30 degrees for a total of 60 degrees. From 2 to 3 would be another 30 degrees, and that's 90 degrees. It will be 3 o'clock after a 90-degree clockwise rotation. If it starts at 3 o'clock and rotates 150 degrees counterclockwise around point P, what time will it be? Well, let's see. We're going counterclockwise now. We have to go 150 degrees, which is right here. It will be 10 o'clock after a 150-degree counterclockwise rotation. Translating points with a compass. A rotation is a geometric transformation that rotates a figure clockwise or counterclockwise around a given point at a specific angle. All rotations are defined by the point, the angle, and the direction of rotation. In the example on the right, triangle ABC is rotated 90 degrees counterclockwise around point P to form the image, triangle A', B', C'. Notice the two directions, clockwise and counterclockwise, and the rotation would look like this. Let's see how this is done using a straight edge, protractor, and compass. Rotating a figure with a protractor and compass. Rotate triangle ABC 90 degrees counterclockwise around point P. First, draw lines from the center of rotation, P, to each vertex of the figure using the straight edge of the protractor. Like so. Now use a protractor to measure 90 degrees counterclockwise from each of these lines. Don't forget the directions, clockwise and counterclockwise. So our first will be rotated to here. Now draw each line, then use a compass to find the new vertices. Like so. That's how we found A'. Now let's find B'. Again, making the 90-degree counterclockwise mark, drawing our line, using our compass to measure the distance. Now we have B'. Now let's do the same for C'. Making the 90-degree counterclockwise mark, drawing our line, and then measuring the distance using a compass. We make our mark at C'. Now we simply connect the vertices, and now we have the image, triangle A', B', C'. Rotational symmetry. A figure in a plane has rotational symmetry if the figure can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. The minimum amount of rotation required for a figure to be mapped onto itself is called the magnitude of rotation. The point that is equidistant from each vertex is called the center of symmetry. First, draw the lines of symmetry. Each line must connect to at least one vertex. Lines of symmetry were discussed in depth in a previous lesson. For example, we have two lines here. Now label the center point P. How many lines, N, are there from P to the vertices? Well, here's 1, 2, 3, and 4. so n, in this case, equals 4. To calculate the magnitude of rotation, we take 360 degrees and divide it by n. 360 degrees divided by 4 is 90 degrees, so the magnitude of rotation is 90 degrees. A square has rotational symmetry with a magnitude of rotation equal to 90 degrees. Alright, now we're ready to do further examples.